have an evening like this, where the previous winners of the Honours Scholarship typically speak. And it's our pleasure to have Michael Gerard and Tinula is here somewhere, Karyo-sam, who were last year's winners, and they're going to speak to us tonight. Michael is going to talk about what it says up there, elastic registration of NMR spectra, and I think he's ready to start talking. So, Michael, over to you. You've got an eager audience here.
Okay, thanks, Alan, and I'd like to thank the Statistical Society of Western Australia again for awarding me this scholarship last year and for inviting me back this year to give this talk. So tonight I'm going to be talking about registration of functional data, and in particular describe the method of elastic registration. And then I'm going to finish up by showing some results of elastic registration when used on the following dataset shown in the top figure. So what we're looking at is a sample of 200 NMR urine spectra from patients with autism spectrum disorders. And this is a group of disorders which includes autism and Asperger's syndrome. And this dataset was made available to me by Dr. Torben Kim Hover from Fiona Stanley Hospital here in Perth, or in Perth. Each spectrum graphs intensity as a function of frequency and consists of 3 well-defined peaks, which identifies the presence of citric acid in urine. The intensity of each of the peaks is directly proportional to the concentration of the citric acid in the urine cycle. So really the main question we want to answer when looking at this data set is we want to see if do ASDs affect the concentration of citrate in urine. If we can analyze the intensity of the peaks as a sample, we may be able to learn how ASDs affect chemical processes in the body that produce citrate as a byproduct. Now, the interesting thing about this data set is when we look at each spectrum individually, they have this common underlying structure of 3 peaks as shown in the figure below. But when we take a step back and we look at this data set from the perspective of the sample whole, it appears that we've lost that structure. So the first question we immediately ask is, why has this happened? And the data set looks this way due to a common phenomenon in functional data where we have 2 distinct forms of variation mixed together. And these are known as amplitude and phase variation. So amplitude variation is characterized by vertical differences in the y-axis of functions, whereas phase variation is seen as horizontal differences in the x-axis. So for our data set, amplitude variation is the differences in the intensity of the peaks, and phase variation is the differences in frequencies, or their locations on the x-axis. Now what happens is that these 2 forms of variation occur simultaneously and become entangled. And when this happens, it becomes impossible to distinguish amplitude from phase variation. And that's why we see, and that's why the dataset has this form here. We have the amplitude variation and the intensity of the peaks, but we also have that phase variation, which causes the peaks to overlap. And we lose that structure that we had in the data. Now, if we ignore the fact that we actually have a mixture of variation, this can lead to erroneous analysis, as shown by the sample mean. Now, immediately when we look at the sample mean of our 200 spectra here, we can see something's going wrong. This does not show, well, it doesn't look like any of our observations in the sense that it doesn't have 3 peaks, and it contradicts what we know about the dataset. This does not represent an NMR spectrum of citrate in urine, and so it's invalid. So to avoid results such as these, we need to account for both amplitude and phase variation in the data, which we do by making the following assumption. We assume that our observations are actually a composition of 2 different functions. So we have the registered function, which shows us only the amplitude variation or the vertical differences. But then we also have a warping function, which only shows us the phase variation. And we also, importantly, we constrain these warping functions to be strictly increasing and bijective. So from this point, what we actually want to do is we want to work backwards. We want to be able to recover the registered functions from our observations. And the way we do that is by computing the inverses of each of our warping functions, which is why we constrain them to be bijective. So their inverses exist and are unique. And then once we compose each of our observations with these inverse warping functions, you can see in the blue part of the equation, we're composing a warping function by its inverse, but that just cancels out. So once we make this composition, we're left with only the registered functions, and they only show us the amplitude variation in the data. And untangling amplitude and phase variation of functions in this way is known as registration. So to demonstrate what registration looks like in practice, we're going to use the following example. In the top right, you see two spectra, which we can clearly see both amplitude and phase variation in their peaks. And what I've done is I've gone ahead and I've computed the inverse warping functions, which will align these two spectra, and these are shown on the left. Now this is how to essentially read warping functions. The dotted line on the main diagonal, that's the identity function, which fixes your spectra in place. They don't move any of the features along the x-axis. So how it works is, the further away a warping function is from that diagonal, the more it will move its corresponding spectrum along the x-axis. Furthermore, if the warping function lies above that diagonal, that means the spectrum is going to shift to the right. Whereas if it lies below, like with the red warping function, that means that the red spectrum is going to shift to the left. Now I'm going to show a video which is going to show some dots be traced over the warping functions and the spectrum. And as that happens, it's going to trace out the registered functions below. So we can see from this point, now they're diverging. The blue spectrum is shifting right, and the red spectrum is shifted left. And the result is that we've had those peaks become aligned on the x-axis. So now what we're seeing is only the vertical variation between our two spectra. So how we actually compute these inverse warping functions is we frame registration as an optimization problem. So we choose a dissimilarity measure, which I'll denote by delta. And then we also choose a fixed function called a template. And we're going to independently align everything to the template. The inverse warping function of each observation is the minimizer with respect to the dissimilarity between the template and the aligned function. So this is our overall framework of registration, which can be summarized in the following three stages. You start with your unaligned spectra, and you choose a dissimilarity and a template. Then you compute your inverse warping functions with respect to that dissimilarity and template. And the final step is to compose each of your observations with the inverse warping functions. And then what we're left is the registered functions that only show us the amplitude variation. So to reiterate, we want to take this data set and apply that registration framework such that we can, hopefully, when we take our registered spectra, we recover this common underlying structure in the data. Now, there's many different methods of registration, but the particular method that I looked at during my honors project is known as elastic registration. And this first appeared in a paper written 11 years ago by authors Shirastava and Steve Marin. Now, to describe this registration method, we need to know two things. What's the dissimilarity measure and what's the template? So the dissimilarity measure is known as the Fisher-Rao metric, and it's given by this equation on the left. And you'll notice it's quite similar to the standard L2 metric, except we've made this funny transformation of our functions, where we take the sign of the first derivative and divide by the square root of the absolute value of the first derivative. Now, this transformation makes it so the Fisher-Rao metric satisfies a special property, which is known as the warping invariance property. And essentially what it means is that you can take two functions, and if you compose them or move them by the same warping function, their distance is preserved. This is a nice theoretical property that makes sense when you think about registration. If you warp two functions by the same amount, you're preserving their pointwise correspondence, and so their registration should be the same. Another way to frame this is to say that the Fisher-Rao metric is elastic, and that's where the name elastic registration came from. So that's the dissimilarity measure. Now, the template is a bit more complex and can't be written as a single equation as you would with the sample mean. In fact, the template of elastic registration is actually defined to be a shape mean, where the concept of shape is extrapolated from the following definition by the statistician David G. Kendall. And here, Kendall is defining the shape of objects in Euclidean space. And he says, shape is what remains after quotienting out translations, rotations, and reflections. And he goes on to say that any combination of these, he calls a shape-preserving transformation. So let's dig a bit deeper and see what Kendall was trying to say. So picture a square in the plane. Now what we can do is we can take that square and we can translate it. We could also rotate it, and we could also perform a number of reflections. And notice how after performing each of these transformations, the square looks the same as it did before. So this is the what remains part of the definition, the salient features that allow us to recognize that this is a square remains the same. Now, quotienting out, we have to go a step further. So denote by O to be a subset of points in Euclidean space that define some geometric object, like the square. What Kendall's idea was is to define the shape class of this object as the set of all of its images under all possible shape-preserving transformations. In a sense, this gives us a mathematical representation for the shape of that object, because all objects in the same shape class have those same properties as I showed in the slide before. Now, I've digressed a bit from functions here, but this is the main idea. Using this representation of shape, we want to define a metric on the set of shape classes and be able to compute distances between the shapes of objects. In doing so, this will allow us to compute statistics of shape, and this is where the field of statistical shape analysis came to be. Now, with this in mind, the idea of elastic registration is to apply Kendall's definition of shape to functions and compute a shape mean as the template. And this can be achieved by recognizing that the shape-preserving transformations of functions are given by the warping functions. In the video, the animation I showed before, we showed that when we compose the spectra by the warping functions, we're actually preserving the number of modes and the intensities of the peaks. We're not changing its outline or its form, so it looks the same. Now, using this, we define the shape of a function x to just be the set of all warped versions of itself. And this shape class is then characterized by the number of modes and the amplitude of x. So this is an example of some functions which belong to the same shape class. Notice how they all have the same number of modes and that those modes have the same heights. The only difference is that their locations on the x-axis have changed. But the overall form or the shape of the function is the same. So this is the overall framework that elastic registration uses to compute this shape mean. We start in the top left with our unaligned functions, and we consider their shape classes, which is again just the set of all warped versions of themselves. We then work in the shape space, which is the set of all shape classes. And using the Fisher-Rao metric, we define a shape metric between shape classes, which is just defined to be the minimum pairwise distances between members of those two sets. Now, in order to compute a shape mean, we generalize the principle of least squares using this shape metric. So we minimize the sum of squared shape distances from our observations. And the shape class which achieves this minimum is known as the Kasha mean. From here, the last step is to choose a particular member of this Kasha mean as a template, and then we can define that to be our shape mean. In elastic registration, we choose this member to be the function that such that its features are located at the average X values with respect to our sample. So when we look at all this, we can note that this is a lot more computation than just taking the sample mean. And it's a nice theory, but how does that actually translate into practice? It actually works really well. So on the left, we have a data set that we'd like to analyze. And on the right, the black curve is its shape mean as computed by elastic registration. And now the X's mark the locations of peaks with respect to the spectra on the left. And we can see that the frequencies of the shape means peaks roughly lie in the center with respect to the sample. So not only are we getting a function that has the average intensities of the peaks, we also have the average frequencies as well. And immediately we can see why the shape mean would be a much more appropriate template to be used than the sample mean, which is the conventional template used in registration methods. So now we're going to move on to the results. So what we did was we compared elastic registration of this data set to two popular methods known as IcoShift and PTW. And this is how IcoShift and PTW performed. And immediately we noticed that it's not great. I mean, clearly we still have a number of peaks that are misaligned. And I mean, it's still just a mess. There's still plenty of phase variation mixed in with the amplitude variation. This is not what we'd like to see. So IcoShift and PTW are characterized by these traits. For IcoShift, the dissimilarity is the cross correlation, and the template is surprisingly the sample mean, which had that horrible shape that I showed earlier. For PTW, the dissimilarity is the L2 metric, and also the sample mean is a template. Now, what's also interesting feature about these two methods is that they constrain the warping functions to be of a particular class. So IcoShift constrains the warping functions to be translations, and PTW constrains them to be linear functions of frequency. And perhaps that's why they don't work as well, is maybe the phase variation isn't just a simple constant shift or a linear function. So in comparison, this is how elastic registration performed. And we can see immediately that elastic registration has correctly aligned the three peaks of all of our spectra. And now we can clearly see that well-defined shape that we knew was hiding behind that mess. And what's interesting too is we can look at the warping functions and we can say that this is a better, more accurate representation of the true phase variation in the data. And the interesting thing to note is that these warping functions aren't linear or translations. A lot of them are actually curved, which suggests that the phase variation is nonlinear, which means that the spectra are actually being compressed or stretched along the x-axis. The thing we notice is that the warping functions look fairly symmetrical about the main diagonal, which means that there seems to be an equal proportion of spectra shifting right and an equal proportion of spectra shifting left. So now we can fill in the gap and we can compare our three methods. And I've also, just of interest, I've written the time it takes for each method to complete in seconds. So we can see that elastic registration is much, much slower than IcoShift and PTW. In fact, it's 1,500 times slower than IcoShift, but the payoff is we actually get correctly aligned spectra across the sample. A different way we can validate these results is by tracking the locations of peaks before and after registration. So in the top left is a scatter plot, in which each cross marks the location of a peak for each spectrum. We have three colors and each color corresponds to one of the three peaks. Now, what we want to see from a registration method is that the crosses of each color are aligned in nice vertical columns along the x-axis. And we can see the only method where we actually achieve this is with elastic registration. If we look at IcoShift and PTW, and actually especially IcoShift, you can see that a number of the pink crosses have been moved over towards the middle section where all the blue crosses are. And that indicates there's been a lot of misaligned peaks in the sample. And similarly, you can see the same with PTW. Although it performs better than IcoShift, we still have a number of misalignments. Okay, so in summary, whilst elastic registration is a much slower method than IcoShift and PTW, it's far more superior in terms of peak alignment, and that's likely due to using and constructing the shape mean as a template rather than the standard sample mean, because it's more compatible with our observations. It's also likely due to the fact that the phase variation is non-linear and not a constant or linear function of frequency. And so IcoShift and PTW weren't able to really define the phase variation or encapsulate the true phase variation we saw in the data. That's it.
Thank you very much, Michael. I don't know if you heard the tail end of the applause there. I couldn't switch the microphone on fast enough, but I can assure you the audience was definitely applauding. We've got time for some questions, which I will repeat. One from the back is George. Do you want the microphone? Would that be best? He won't hear you otherwise.
I'm not sure if I'm audible.
Yep.
I'm coming through. Okay, good. Thank you. I was just wondering, is this written in R, the routine?
So the routine is currently written in R, Python, and MATLAB. Okay. There's been a number of libraries written across multiple softwares. For the figures in this talk, they were actually taken from, the computations were done in each one of them, in each of R, Python, and MATLAB.
Okay. And do any of the languages utilize parallel computation for it, or are the data dependent?
I believe Python uses parallel computation, but I don't think that, I'm not sure if R and MATLAB do. I don't think they do from what I've seen, only Python, I would say.
Fair enough. I guess I had one question which is possibly related. For the size of the data and the computation time, I guess, in relation to that, is this representative of a sort of real world sample size, or the real world amount of data that you might do this computation on?
So this was quite a large data set. In fact, this is actually a subset of a much bigger set. So this was 200 spectra measured at roughly 500 points of frequency. If you look at the entire spectrum, or the entire frequency range, each spectrum was measured at 28,000 points of frequency. And in fact, the data matrix was so wide that the registration algorithm wasn't able to complete. So the major pitfall of elastic registration is that extra computation time it takes to compute the shape mean. It seems to be lacking in that respect with respect to other registration methods. But in terms of your question, I guess for a real world data set, I would say this was probably slightly smaller. And I think from other NMR data sets that I've seen, they can run up to the thousands of observations measured at tens of thousands of frequency points.
Yeah, because the individual who made the data available, I used to work in the same center there, and some of the samples were much larger and some of them were much, much smaller, but indeed there would usually be many more points of frequency than 500. But sometimes you only had 7 samples.
Yes, exactly. Yep.
Anyway, thank you.
Thank you. Anybody else? John Henches.
Thank you for your talk. It's actually very good. But so my question is a slightly negative one. You've actually shown that if you're fitting a model with more parameters, then it is a better fit. And that's, in one sense, not surprising, because your transformations, which give you your elastic transformations, is actually very, very flexible. To what extent is this improvement significantly better given the extra degrees of freedom that you've added to the model that you're fitting?
So you mean because we don't have any as I said, with IcoShift and PTW, how they constrain the warping functions to be translations and linear. And with elastic registration, they're not constrained.
Well, that's right. Your elastic transformations have got far fewer constraints than the other methods you showed.
Yes.
You know, your first two methods had effectively for each data set, they had either 1 or 2 degrees of freedom in your warping function.
Yep.
Now you've done something with many more degrees of freedom, so you would expect it to fit the data better.
Mm-hmm.
Is it significantly better?
Well, the problem is with increasing the degrees of freedom is you have something that is called the pinching effect. So if you actually, if you don't constrain your functions too much, what can happen is you can get over warping, which I think is what you're saying, where you can arbitrarily minimize the dissimilarity between your template and your aligned functions. I mean, in this case here, showing the difference between elastic and IcoShift, I mean, I guess, you know, we can see that elastic registration has actually, you know, correctly aligned them. But in terms of adding more degrees of freedom, I'm not sure to what extent, like with how many degrees of freedom you get certain improvements. I mean, as you increase the degrees of freedom on your warping functions, I'm sure you can capture the phase variation, but then you're right in the sense that you could overfit that and your phase variation might have fewer degrees of freedom. But to be honest, I'm not sure as you increase the degrees of freedom what the extent of the improvements are. As far as I know, elastic registration, there are no constraints, and whatever the phase variation is, it will just go and find that through the warping functions. I'm sorry if I didn't answer your question.
Okay, but
He won't, hang on a second. You'll need that.
I suppose my question is that, is the improvement in fit commensurate with the extra freedom or degrees of freedom that you're allowing in your model there? Or, you know, is the improvement better than what you would expect simply from a degrees of freedom type of argument? So in other words, is it significant? I suspect it is, by the way, but your talk hasn't really addressed that.
Okay, I mean, I guess the only thing I can say from this one is that with IcoShift, you're fitting, and with PTW, you're fitting something with fewer degrees of freedom and you're not getting the registration properly. And then with elastic registration, as you get higher degrees of freedom, you get these non-linear functions, you're able to properly register the spectra. So I would say it is significant because you're going from something which are not registered to something that's registered.
Thanks, Michael. I have a so we're having a discussion about whether I'm allowed to talk or not. I had 2 questions. One arising out of what John just said. There is, of course, a constraint, isn't there, of monotonicity of the warping function. Is that correct? Yeah.
Yes,
so there is a constraint.
Yeah.
And the other thing I wanted to ask was about your Karcher mean. The word mean always sort of raises with me the question of how robust is this, and is there? I noticed that peaks sort of hop, as it were. It looks on some of the pictures, it looks as if a peak is in the wrong place, and it's sort of it's a discrete question about whether a peak is in the right place or not, and that might have to do with a robustness question. So
yes,
have you looked at that at all?
Yes, that's a good question. Actually, one of the issues with elastic registration is how sensitive it is to the shape of the spectra. In this case, the Karcher mean actually works quite well because each spectrum has 3 well-defined peaks. So they all have that common shape. But then, of course, there's always the question, well, maybe you get a data set which has, you know, some spectra have 2 peaks, maybe some have 4, or, you know, in general, your functions. And I guess in terms of robustness, it comes down to the question of the cost function you're minimizing. So there's been some variations of this method where instead of minimizing the sum of the squared distances, you just take the sum of the distances in the same way you minimize the absolute value rather than, the sum of square distances. If you want to do your L2 metric versus L1 metric. So yeah, I've looked into perhaps ways to make this method more robust, and one of them is varying that cost function. But here, elastic registration does work quite well only because they have a common shape. But it's an interesting question to ask about this method. If you introduce spectra with different shapes, then how well does the shape mean turn out?
Okay, thank you, Michael. I think we probably have to say goodbye to you now because you won't be able to hear us, and to thank you very much for your talk, which was great, met here with a great deal of interest.
Thank you. Thanks, everyone.
I hope you were able to hear that.
Yeah, no, I could hear that. Thank you.
Good. So we'd invite you, we'd love you to come and have dinner with us, but it's a long way.
Yeah.
Thank you for taking the time to talk to us from Canberra.
Okay.
Bye,
thanks,
Michael.
Alan. Bye.
So Mike. Yep. Okay. Hopefully this mic works as well. That was very good pronunciation of my last name for a first try. So yeah. Just as Michael said, just want to thank Stats Society for having me present today, and as well as the scholarship for me and Michael both last year as well, and as well as my supervisors from last year, Inga and Bervin. And thank you for coming as well. The last little thank you and thing I want to say is just to the Department of Primary Industries and Regional Development, so DPIRD for short. This whole research problem data comes from them, and the initial ideas also resides with them. And all throughout last year, they helped me with, understanding somewhat of the wheat production, the definitions, the terms, and like they provide a great industrial perspective to some of our results as well. So I wouldn't be able to get through most of my research if it was for them and my supervisors. So for my research problem really lies in the side of applied sort of issues. And so for us to understand what the importance and why we're doing this and everything behind it, I sort of want to give my understanding of the wheat production and how its management works, my years worth of introduction into it. So the best way to summarize it is just to go through this little flow chart I made for myself initially, all the way back to the start of last year. So I'll try and relay my information to you guys. So for the word sowing you're going to hear all throughout this talk. Sowing just simply refers to when we plant, or when we plant that seed, and each year you're going to have a certain sowing period of time. That sowing period depends on when environmental conditions such as temperature, rainfall, and all other types of environmental factors are as optimal for an agronomist and for a farmer. Now, historically, the sowing period has always been between mid-April to early August. Correct me if I'm wrong. If anyone else has any understandings of the wheat industry, but sorry. And late June? Yeah. Okay, perfect. And climate change has had a say in all of that as well. So sowing periods have been pushed to a bit of an earlier times as well, which we'll touch on a bit at the end as well. And each sowing period in each year has different amount of sowing times as well. So a farmer or a grower can say, oh, okay, I want to sow on April 29th or July a day, given a day. Now, through research and development and genetic mutation, there's a whole heap amount of wheat varieties that exist out there. I think it's about 1,000 or so. And to make things easier, the industry agronomists sort of said, okay, why don't we group these wheat varieties and say on a particular characteristic and say, okay, this particular sowing time should look to sow these types of varieties. Now, previously, and I think still, again, correct me if I'm wrong, the maturity definition they give is based on flowering time response to sowing time. So flowering time pertains to, I think, when you harvest the seed, I think so. And that's what I've always understood it as. So basically, you're just looking at, okay, when I plant that seed of wheat variety, how many days does it take for me to flower? That's what that previous maturity definition is. But when you look to quantify your wheat variety or wheat production, you're really looking at one important factor, which is yield. And yield is missing in this maturity group definition, and it's missing for a certain reason. It's hard to really group, and it's tried to be done throughout the industry, but they haven't taken a statistical approach to things. So that's where Deepa and some of the people from the grains industry team came and said, okay, can we sort of change our maturity group definition to yield response based on sowing time? So try to sort of visualize what's going on. I made just simple, like what we want to approach to. So we're going to see a lot of these response curves with many different lines here and forward. So first thing to look for is our y-axis, just yield, and we have different sowing times from mid-April to end of June, and could go to July as well. I just made steps for us to understand what we want to see. When we see like smaller lines, especially dashed lines, just those really refer to just individual varieties. And for my like visually understanding, we sometimes create these thicker lines which just refer to the mean response curve for a certain group. So take for example, if we wanted to sow on the 15th or somewhere around the 22nd of April, we would choose a variety from that blue group and so forth. That's what we want to aim to, and it's all based on yield response, no flowering time, nothing. We don't want to take that into account. So that's what we want to hope to get to. It isn't as easy as that, but we can get to it. So working with wheat variety and grains data was a unique experience, I say the least. It was fun at times, a bit of a struggle at times as well. So Deepa gave us 4 years of data. I think it was from 2015 to 2018, right? And each year the sowing times weren't consistent across all 4 years, so different sowing times, but between the same period that we referred to historically. So there's inconsistent sort of sowing times, and the biggest one that we'll come to as well is that there was only 34 varieties that were consistent all across all 4 years. So that I'll touch on a lot more later, but that's something to keep in mind as well. Each year did have 8 times the sowing, except for 2015, we did have to remove one, which I can go into later if you have any questions about it. So 8 times the sowing for each year. Number of varieties do decrease as we go across, but that's right. We still have a lot of observations, a lot of yield responses, and obviously Deepa wants to group them based on their yield responses. The initial idea was, okay, or initial approach that Deepa came to us was, can we just put together all 4 years of data and see how we get 4, 5, 6 different groups and see what we can work with that. Is there at each sowing period a group of varieties that pertain to the highest yielding? Now we think, how can we do that statistically? We just took a k-means clustering approach. Now for us, we're looking at amplitude or the height of the response curve, and there was a sort of understanding that we wanted to look at the shape as well, so we can utilize 2 distance measures of Euclidean and Pearson's correlation score as well. So we combine these 4 years of data, and the question with obviously k-means clustering is, what is the optimal amount? They say we don't like that word as much, but what is the optimal k value for our k-means clustering? But it really depends for me, always on context, right? What's your research? What's your aim? For us, we're just going to have a look at these response curve graphs. Can we identify, like for each sowing period, is there a certain group that we can confidently say has the highest amount or pertains to the highest amount of yield for each group? If so, that's good with K, but you can't confidently say it, then we can move on with that K value. So that's how we choose our K values and k-means clustering for our context. So we've got 4 years of data. This is one of the most interesting results we got all throughout last year. So this is just a Euclidean distance 4-cluster approach for all years of data, 4 years of data. Now I've just separated them to 1, 2, 3, 4 clusters. But what I've also done is each color lines is the 4 years of data. So as you can see, each year is quite different to each responses. So 2015, cluster 3, there is a few 2016 in cluster 3 as well, but we can confidently say this means that perhaps taking a full 4-year approach is not the best way to sort of separate our varieties and based on their yield responses as well. So perhaps we go, okay, we break things down a bit more. We take a year-by-year approach. We figure out different technique or approach that works to our aim. Then we come back and look at maybe the variety allocation and does this work? So if I had, 40, maybe now I would go through all 4 years and, it would be work. We could talk about it the whole time, but I'll just stick with 2015 and we'll have a look at the different sort of methods and techniques we took. We already have 2 different distance measures that we can take, right? So Euclidean and Pearson correlation. What other techniques can we do with our data set? What other handling of the data matrix can we do to sort of work to our aim? So that's what we said. So having a closer look at 2015, these red dashed lines indicate just each slowing time. And again, we removed one of them. I think it was the one between 119 and 135. So right away we see, well, as I've been saying for a while, is that our importance really lies on the height or the yield, top yield measures, right? So you can see in the later stages, maybe slowing time 173, 153, and maybe the argument for 143 as well, that the variability throughout, the variability of the yield measures on those slowing times aren't as much as you see in the initial 3 or 4 slowing times. So perhaps relaxing our clustering algorithm to perhaps just removing those slowing times and just saying, okay, just have a look at the first 5 or first 4. But there's a lot of variation. You could just remove 173 and see where we go. So again, emphasis on we just explore what works for our aim and we move forward. Another thing as we look closer into this data and the slowing times with them is perhaps there's a bit of an argument to make that the first 2 slowing times have the same varieties that are the highest. Maybe the next 2 time slowings look very similar like that. So propose this new idea where this is just an example of it, is where we sort of group the time of slowings together. So what I mean by that is we have group A, B, C. So this is just one example, but you do k-means clustering algorithm. K's you can range from 1 to however many you want for A, then to B, then to C. And you can go forward with that. You can try and match these different clustering algorithms together. So that's another way we can take a look at these things. Now, the third one I'm sort of going to propose is what we've seen from the data before is that there are a lot of varieties that are consistently low measuring yield. So I think it was about a month or 2 left in my honors project. I was having a talk with one of the deeper data people, and they were just saying, oh, even though you have about 100 varieties, 80 varieties sometimes, when a farmer or grower, and during their sowing period, they only have like 20 varieties with them. And so let's say, take for example, 2022, right? He wants to now start sowing his wheat varieties. He would have genetically produced them or how it goes at the end of 2021 and only has 20 with them. So we go, okay, why are we always focusing on 100 or 80 of these varieties? Why don't we just find what are the consistently high yielding varieties throughout each sowing time? Maybe just break it in. Maybe have like 20, 15 odd varieties. So that's our third sort of technique in it, things where we, at each sowing time, we maybe put a quantile number and we say, okay, if at any of these sowing times, a variety shows a high yielding measure, we'll keep it in our data matrix. So I think this is the 90th quantile we put here, and we've removed, we've got down to 21 varieties. So there's a lot. It looks a lot cleaner as well. We can work with it a lot easier. So with this technique as well, we can go back to the other 2 techniques and remove sowing times, so we can group sowing times. So there's a lot of exploration involved. Remember, we do have 4 years of data, and each year is very, very different to each other. So it's much of the races was just working with it, having a look at response curves, having a look at that, or groupings, does it work? What is the right K value? It's a lot of exploration. And what we ended up with, oh yes, so even with separation, I sort of was getting confused at times. Okay, what am I looking for? How can I say, okay, this looks correct and this doesn't? And there was always this question I had with even Ingo, but it was like, what do you mean by right? What do you mean by this is what we're looking for? So I sort of set this criteria. I remember saying, okay, the number one most important thing was, okay, if any of these like groupings show at a specific time an explicit high yielding cluster, then we're good with that. We can say, okay, this technique, this method, it works for this certain year. And the other thing was, does each group have a different mean response curve in terms of its shape? So this is what we ended up with. Now, this is just one of the variations. I remember for 2018, had 4 different techniques that worked. And with 2017, it was 3, but the other 2015 and 16 only had 2. So this is just an example of what we can end up with. For 2015 and 16, it was both correlation distances that worked, 17, 18 Euclidean, 15, 16, and 18 both utilized removing varieties based on a percentile value. So that last method did work out for us, but unfortunately came in a month or 2 at the end. But so we got this at the end. Now, the last part, the tricky part of our whole research is, okay, what varieties are consistent across all 4 years given a sowing period time? So to visually sort of comprehend this, it's like if I had 2015, 16, 17, just all vertically going down. And let's say between sowing times 100 and 120, cluster 1 in 2015 would be the highest yielding varieties. So are those varieties the same in 2016 when it looks like cluster 3 is the highest yielding cluster group? Same for 2017 when it's cluster 1, and same for 2018 cluster 1 as well. So are those the same exact, or are there varieties in there that are the same? Now, so going back to, there was only 34 varieties that were consistent across all 4 years. So that's our little issue here that we run into with everything. Fortunately, there was only one variety that was consistent there for all 4 years, given a sowing time and a sowing the highest group. So I think there was, but at least when we looked at, okay, at least 2 years were consistent, there was about 22. And for 3 years, there was about 5. So this is the one issue that we did run into our research at the end. It was, we're sad to see, but we got one variety that, however, there were some recommendations, some good recommendations I was able to make towards DPERT. One particular one is the early times of sowing. So I think we saw in many of our response curves around mid-April, end of April, most of them with a particular high yield response, responsing for varieties. Basically, still in the industry, they're still looking at, middle of July, June, those types of sowing times. They're still scared a bit to go to look at those times of sowing. So we did sort of, with our work, with our research, we were able to show, okay, maybe we should be using these April early sowing times as well. And I think it was an email from Ben Rudolph, one of the data experts. It was like during March. He said, yeah, okay, he had a good read of my thesis. He said, okay, I'm going to sort of try and conduct this trial again, starting, I think, from 2022, basically saying, I'm going to scrap the whole idea of using 180, 90 varieties that he did for those 4 years, and he's going to try and use the consistent varieties that I've provided that show at least the high yielding measures and were consistent somewhat in our results. So being able to make those recommendations, hopefully we can explore other different types of grain yielded responses as well. But that was all for my talk. Thank you very much for your time and attention. Yes.
I've got one. The clusters interpretable? I mean, could you say, all the ones developed by this company were all in cluster 1, and the ones developed by this company in cluster 2, or how does that work?
They weren't, yeah, it's like at first I thought they would be interpreted as that, like as you're saying, but the idea sort of goes down as the consistency of varieties just, oh yeah. So that was our biggest issue that we ran
One
into.
lives in hope.
Yeah, honestly, yeah.
Just wondering why you chose cluster analysis instead of regression.
Great question. So actually,
It looked to me like you had multi-level modeling that was perfect.
I agree. And so the first 2-3 months of my research, which I did not talk about at all, and I'm sure we could lovely talk about this for a long time, was we did quadratic penalized spline regression with a random effect modeling and everything. It just didn't work out because we only had 8 times assignment to work through our model. So we sort of scrapped that idea after 2-3 months of explorations, discussing a lot. And the idea was given to us by a team member in the Grains department from DPERT. And then we had to just move on straight to clustering, because the idea was to model and then take the fitted responses or coefficients of those and then try and cluster and group them based on that. And we just couldn't get the regression modeling down.
You mean that the data did not produce a good model, or was very—
That's exactly significant. No, it was an overfit, and we lost a lot of the variability with that you could see within that 2015 data, especially, and it just became all the same lines, just difference in that, and they lost a lot of variability because of that regression. So in terms of future work, I would love to go back and explore what went wrong and change up a method in terms of that regression as well, but it's just something that just did not work out first 2-3 months. Yeah. No worries.
People, farmers tend to often talk about the season being late this year or early this year.
Yeah.
Which would mean that the weather pattern shifted from one year to the
Yes.
next.
Yeah.
Now, given that you've just heard a talk about registering the handling this issue of things, whether it's the phase changes.
Yeah.
Would you consider something like that? I'm not sure it would be exactly the same.
Yeah.
Exactly the same.
Yeah.
And apart to your time points. So I know there are constraints, but did you consider something like that?
I consider, so.
And given that you heard the previous talk, would you do it now?
So me and Michael were close friends all throughout of our last year and during our thesis, same supervisors as well. And I think the first time I heard about his research, it fully went to us maybe middle of the year. And I go, wait a minute, like, why haven't, I thought of this all like this? But it was, I thought about it, but just thought about it too late in terms of, yeah. But I was like, oh, I should have looked at something like this at least. So yeah, I completely agree. Yeah, completely agree.
I want to ask you about not so much this stuff,
Yeah.
but your interaction with DPERT. So you're a data analyst.
Yeah.
You have now an industry or government partner.
Yeah.
Can you talk about what was really great about that, and possibly what you had to work really hard on to make this successful?
Yeah. The great was just an industrial understanding and a perspective in terms of any of my results, any little slight like trends or anything we see that, oh, that's that. Oh, that's that. And I'm like, oh, okay, I did not know this. Oh, that's when frosting occurred, this. So removing of a sowing time in 2015 wouldn't have occurred. It wouldn't even thought to us if it weren't for the understanding, oh, that was a frosting when we were at a specific time in this. So they really knew and understood the data. The troubles to say was, I could remember this time particularly, it was like that criteria I had like a based on was, I was struggling to sort of understand exactly what DPERT wanted at times. So, first month or so, I thought I had great results and I'd gone in and went, oh, have a look at this. And then they're like, oh, actually, we want something like this. Oh, hold on. And it just changes month in and month after. Now, go tell Ingram and Bevan what they told me. Like, wait, what? Like, what's going on here? Like, something's changed. Like, I obviously understand it from an industrial perspective. They want the best results possible. They want, what they want. So then I built this criteria like later on. I was like, okay, I need to understand what I want and what I want to get out of this and what I want to aim for. So then the thesis I'm writing isn't changing every month or two as well. So that was sort of the biggest trouble and things like that. But yeah, I had great relationships with them, all of them as well. So yeah, that's good. Thank you very much.
Thank you very much.